Welcome to this fascinating journey into developmental biology. Today, we're going to explore one of the most incredible survival mechanisms in the human body, compensatory regeneration. We will discover how certain organs, like the liver, can bounce back from massive damage or surgical removal, not by starting from scratch, but by scaling up what remains. Let us dive in. To begin our journey into developmental biology, let us imagine you are managing a busy factory. Suddenly, a third of your workforce has to leave. You do not tear down the building and rebuild it, nor do you hire completely untrained interns. Instead, your remaining experienced workers simply work overtime, and eventually they train a few new people just like themselves to fill the gaps. In the human body, this is exactly how your liver responds to severe damage. It does not grow back a missing piece from scratch. The remaining mature cells simply expand their workload. Now that we have an intuitive picture, let us look at the formal biological definition. Compensatory regeneration is a highly specialized form of tissue repair. Unlike other forms of regeneration, where cells must forget their identity and revert to an undifferentiated state called a blastema, the cells here always remember exactly who they are. A mature liver cell, called a hepatocyte, remains a fully functioning liver cell even while it is actively dividing. It continues to filter toxins and produce vital proteins, ensuring the organism survives while the repair process is happening simultaneously. Understanding that cells remember their identity leads us to how the organ actually regains its size. When a piece of the liver is removed, the body does not try to sculpt the exact missing lobe. It doesn't care about the original shape. It only cares about the total volume and function. The remaining lobes simply scale up. This remarkable recovery relies on two processes working in perfect harmony. First, we have hypertrophy, which is the physical enlargement of the existing cells. Second, we have hyperplasia, which is the cellular division that increases the total number of cells. This remarkable cellular mechanism is not just a biological curiosity. It has profound real-world applications. The existence of compensatory regeneration is the sole reason living donor liver transplants are possible today. Because of this ability, a healthy person can donate up to 70% of their liver to save a dying patient, and within weeks, both livers will grow to a fully functional size. Furthermore, even if you never donate an organ, this process protects you every single day. It constantly repairs small portions of tissue damaged by toxins, alcohol, and infections, ensuring your primary filtration system never goes offline. Because this process is so reliable, medical professionals can actually predict it mathematically. The liver cannot grow infinitely. It stops when it reaches its original size. We model this restricted growth using an exponential decay of the missing mass. In this formula, M of T represents the mass of the liver at any given time after surgery. M max is the original healthy mass the body wants to restore. M0 is the starting mass right after the surgery. The constant E is the base of the natural logarithm, common in biological growth. Finally, K is the regeneration rate. If K increases, the liver cells are dividing more aggressively, and the organ regenerates much faster. Now that we have our mathematical model, let us see this formula in action with a concrete example. Suppose a donor has an original liver mass of 1,500 grams, and after donation, they are left with 500 grams. We want to know when they will reach a safe threshold of 1,300 grams, given a rate constant of 0.1. We start by substituting our known values into the equation. The difference between 1,500 and 500 gives us 1,000 grams of missing tissue. We subtract 1,500 from both sides, leaving -200. Dividing by -1,000 isolates our exponential term, giving us 0.2. Taking the natural logarithm of both sides cancels the base e. Finally, dividing by the negative rate constant reveals that it will take approximately 16 days for the donor to recover a highly functional liver mass. This rapid recovery time is incredible, but it brings us to a critical surgical question. How much can we safely remove? Medical guidelines state that a donor must retain at least 30% of their original liver mass to survive the immediate postoperative period. This retained mass keeps the body filtering toxins while regeneration begins. We calculate this using a simple percentage formula. V-keep is the absolute minimum volume of tissue the donor must retain. The 0.30 represents our strict 30% safety threshold. V total is the donor's original healthy liver volume before surgery. If the total volume is larger, the absolute volume they must keep also increases proportionally to maintain safe toxin filtration. Before we move on to the actual donation, let us calculate this absolute minimum baseline for a specific donor. We are given a generous donor who has a total healthy liver volume of 1,800 milliliters. Our goal is to find the exact volume they must keep to survive. We choose our safety threshold formula because it directly applies the medical 30% rule. By multiplying the total volume of 1,800 by 0.30, we find the critical mass. The final answer tells us the donor must keep exactly 540 milliliters of their own liver. Dropping below this physical volume would put the donor's life at severe risk. Once we have secured the donor's safety by calculating the retained volume, we can determine what is available for the recipient. This is done using a straightforward subtraction formula. V-remove represents the maximum safe volume of liver tissue that the surgeon can extract. V-total is the starting healthy volume, and V-keep is the mandatory safe volume we just calculated. By subtracting what must be kept from what we started with, we ensure we do not cross the dangerous threshold of liver failure. If the retained volume requirement increases due to medical caution, the maximum removable volume will physically decrease, leaving less tissue for the transplant recipient. With our subtraction formula ready, let us find out exactly how much liver tissue this donor can provide. We know the total starting volume is 1,800 milliliters, and we just calculated that the donor must keep 540 milliliters. We use the subtraction approach to find the difference between total capacity and the safety baseline. By subtracting 540 from 1,800, we get our result. This final answer of 1,260 milliliters is the exact physical amount of liver tissue the surgeon can safely remove and transplant into the recipient, knowing that compensatory regeneration will restore both livers over the coming weeks. We have calculated the volumes and the recovery time, so let us now visualize exactly what this looks like inside the body. On screen, you are looking at a 3-stage schematic of liver regeneration. On the far left, we see a healthy liver with its original volume and distinct lobes. Moving to the middle stage, representing the immediate post-surgery state, you can see the right lobe has been completely removed, leaving a significant deficit. Finally, look at the third stage on the right. Notice how the liver has not regrown the missing right lobe into that empty dotted space. Instead, the remaining left lobes have physically enlarged to restore the total volume. This perfectly illustrates that the organ scales up its existing tissue rather than recreating its original shape. As we conclude our exploration, let us review the most critical insights we have uncovered. First, compensatory regeneration is a unique biological safety net that restores organ mass without ever relying on stem cells or forming a blastema. Second, the mature cells, like hepatocytes, never forget their identity. They simply enlarge and divide to handle the extra workload. Third, remember that the body prioritizes function over form, restoring the total volume rather than the exact original shape. Finally, by understanding the mathematics behind this growth, modern medicine can safely perform living donor transplants, turning this incredible biological mechanism into a true lifesaver. You now have a solid understanding of how compensatory regeneration works.